Last two lectures, we discussed about one-dimensional wave and how to describe, our parameters for a wave, and we discussed about the wave equations, and then we talk about the boundary conditions. So we have one wave that hit a surface, okay, the a knot, and then we see that the wave can be transmitted or can be reflected, and how can we calculate what is the amplitude of the reflected and transmitted waves, and also their phases with respect to the incoming wave. Okay, so starting from this lecture, I will talk about that light is actually an electromagnetic wave, and then using the same thing that we described before, we can calculate what is the when a light hit a surface, then it can also be reflected or transmitted, and later you can see it can also be absorbed. Okay, so let us first talk about the electromagnetic waves. Let us first talk about I use electromagnetic waves in vacuum. Okay, so let us consider the case that in the vacuum, so there are no free charge and also there are no free current. So as a result, the equation Maxwell's these four equations becomes something like this. Okay, del dot E equals to 0, del dot B equals to 0, del cross E equals to minus partial B over partial T, del cross B equals to mu 0 epsilon 0 partial E over partial T. Okay, so these are really just what the electromagnetic field, electrical field E, the magnetic field B, and they have to satisfy these equations. And I will soon show you that these are really wave equations. Okay, so how to do that? Okay, so let us look at this del cross E. Okay, so we have four equations. We figure out how to do that. Okay, so this one, we really you can look at the vector analysis. So this equation can be written as del dot E minus del square E. Okay, this Laplacian. Okay, so it looks like that. Okay, so this equation I already discussed in when we talk about vector analysis. Okay, so this is what we have. And you can see that because del dot E is equals to 0, so this side is just negative del square E. Okay, and then because we can look at this, del cross E is really just minus partial B over partial T. So this is del cross minus partial B over partial T. Okay, because one is the position derivative, one is the time derivative. We can move this out. Okay, we can exchange it. Okay, and now we have del cross B. We can from this equation. So what we have is minus mu 0 epsilon 0 partial square of E over partial T square. Okay, so this is what we have for this equation for the electrical field. And from here you can see that this side is really equals to this. Okay, so that really says that we have this equation. Okay, and if we define V as 1 over square root of mu 0 epsilon 0, okay, so the equation will look like this. Okay, so you maybe already look at this equation. Okay, you may realize that this is really a wave equation, and a wave is really propagating, with this speed. Okay, and then we can do exactly the same thing for the b. Okay, we just play with these 4 equations, and we also write del cross b. Okay, we do exactly the same thing. What do you find that the equation looks like this? Okay, it's exactly like E. The only thing is you just replace E with B. Okay. Okay. And then these are really, as I said, these both are really wave equations. And the wave is propagating with this speed. Okay. So if you plug the values of mu 0 and epsilon 0, what do you find that this is really equals to 3 times 10 to 8 meter per second, which is really the speed of light. Okay, so what you really see is that if you have electric field and magnetic field that are propagating in the vacuum, and they are really wave, and that wave is really uh, uh, moving with a speed of light. In other words, okay, light is an electromagnetic wave. Okay, so this is a very important prediction, and you can see that this prediction mainly coming from this displacement term that Maxwell added. So if if there are no such terms, of course that E and B will not be really a wave equation. It will not, if this one is really zero. Okay, if the displacement current is zero, then we will not be able to derive these wave equations. So you can see that it's really Maxwell's really invention of this displacement current. Okay, and really tell us that light is really an electromagnetic wave. Okay, and it also, you can see that when we introduced mu 0 and epsilon 0, they are from these 2 equations, from this electrostatics and also from the magnetostatics. Okay, and we never mentioned what I if we multiply them together, then take square root, then 1 over that square root, we basically get the speed of light. Okay, so you can see that it's really because of the Maxwell's introduction of this displacement current that we have the electromagnetic theory of light. Okay, so this is really very important prediction from Maxwell's equation. So unfortunately, Hertz demonstrated that light is an electromagnetic wave about 10 years after Maxwell's death. So Maxwell didn't really see that his prediction is true. Okay, so this is very important. Okay, just to show you that from these equations we can derive this fact that light is really an electromagnetic wave. Okay, so now once we have this, we want, then I said, we want to, so light is now electromagnetic wave and can be derived by the wave equations, one dimensional, we discussed about that. So now we wanted to see that what happened, the E is the magnetic field is also propagating like a wave, and the B is also propagating like a wave. Okay, so we wanted to see the relation between them. Okay, so now let us first look at a monochromatic plane wave. Okay, so what is the really meaning of monochromatic? We know that the light can have different frequencies, and different frequencies often corresponding different colors. Okay, we have visible light. We have red, we have blue. The waves, the frequency are different. Okay, so monochromatic is really, we say that is the frequency is fixed. Okay, omega. Okay, the plane wave is really just to say that let us assume, okay, so let us say here is x and is y and is z. Okay, so we say it's a plane wave is really the wave is really moving x as later you will see that the the wave is for this case is traveling in the z direction and have no x and y dependence. Okay, so in other words, the electric field and also the magnetic field are uniform over every plane that is perpendicular to the direction of the wave propagation. Okay, okay, so if we can write it because we are talking about a wave that are propagating along the z-axis, we can really write it on the complex component. Okay, this is we described before. Okay, we can we like to use the complex format because that allow us to use these exponential things that often make a calculation easier. Okay, so now we have electric field that can be written as this way is a wave propagating along this z direction with a frequency that is omega. Same thing for the magnetic field. Okay, we can also write it down as B0 EIKZ minus omega t. Okay. Okay. And we also have this omega, the frequency is really the speed, which is c now, speed of light, times the wave number. Okay. So now, because we have del dot E equals to 0 and also del dot B equals to 0, this is, the in the vacuum, let us consider this case. Okay. And, from here you will be able to see that the amplitude really have no z component. Okay, so you can just put this, you do the derivative. Okay, and we know that this E0x has no x dependence. Okay, okay, so if you plug in, and also for the y component. Okay, yeah, y component also, this partial E0 x also have no y dependence, of course. Okay, so if you plug these things into this equation, you will find this. Okay, so the wave is really only on the xy plane. Okay, on the plane that is perpendicular, okay, to the z. So from here, we can, from here there are no z components, so it really says that electromagnetic waves really are transverse wave. Okay, so the electric and also magnetic fields are perpendicular to the direction of the wave propagation. Okay, so that is what we have. Okay, and then we look at the other two equations. Okay, so this is these two equation, and then we look at this equation. Okay, okay, And then, so here, we have this E component, which will only have xy component. B also have xy component. So you plug into this equation, you just do the derivative, okay? And then you compare, x component, the I component from left side and the right side of this equation should be the same. The same for the y component, and the same for the z component. Z component is 0 equals to 0 because there are no z components. Okay, and if you look at the x and y components, you get this. Okay, E0. Okay, so the y component for the electric field is equals to omega times the x component of the magnetic field. And the same thing is K E0 for x component, the electric field x component times K equals to omega times the magnetic field times the y component. Okay. Then we can also look at the last equation, okay, which is del cross B equals to mu 0 epsilon 0 times partial E over partial T. And you will find that that equation also give you exactly reproduce this. Okay, so in this case, the other two equations, they are really equivalent to each other. At the end, we just derive this relation between the xy components of the electric field and the magnetic field. And these two equations, can be written in a vector format. Okay, so this is becomes the B, okay, equals K divided by omega times Z cross E0. Okay, so here just say that because this is monochromatic and also is a plane wave, so the B can be directly calculated from E. Okay, and then you can also see that the B and E, they are in phase. Okay, so that means if the magnetic the electron field, the amplitude is the largest one, and at the same time the magnetic field is also the largest one. So if we really write it down, for example, so this is x, this is y. So let us say if the electric field, okay, is moving along this xz plane. Okay, so here is z. So if the electric field, okay, so let us say E is moving on the x plane. Okay, let us say I just assume E is I can really write down the components. We can say is E0 times cosine omega t minus kz minus omega t, plus some phase. Okay, here I assume the case delta is 0 now. Let us say assume is along the x direction. Okay, and then B, okay, is really just calculated this way. So you will find that the B0, okay, if you look at the amplitude, B0, okay, because this magnitude is really 1, so it's really just this, okay, K divided by omega times E0. Because omega is really K times C, so this is really just 1 over C times E0. Okay, so you see that E and B and E, they are in phase, and their amplitude just different by a factor of 1 over C. Okay, so in other words that the and you can see that if because x E is along the x direction, Z cross x will give us y direction. So B is really moving in the xz plane. Okay, so it's something like this. Okay, so the B field is something like this. Okay, one is on the XZ plane. Okay, so the other one is on the YZ plane. Okay, and they are in phase. Okay, so this magnetic field reached the maximum. The magnetic field also reached the maximum. Okay, and the amplitude is just really just z0 divided by c, and because it's in phase, so this should be also kz minus omega t plus delta, and this is along the y direction. Okay, so this is how it looks like, for a monochromatic plane wave. Okay. Okay. And of course, here, we only talk about a wave that are pointing along the z direction. We can, in reality, it doesn't need to always propagate along the z direction. We can define a general propagation vector. Okay. Let us call it a k. Okay, so this k pointing in the direction of the wave propagation, and the magnitude is just the wave number k. Okay, so now once we have that, okay, we can really write down this wave equation for the no, we write down the vector for the e, which is really just the e0, which is can be a complex number. We have ei k dot r. Okay, so kz, if k is just along the z direction, it just becomes kz. But if k is any direction, okay, then the wave should be written as k dot r. Okay, minus omega t. Okay, this is along the one direction. Okay, so this direction is and we said it is a transverse wave, so this one should equals to 0. Okay, let us. Okay, so there should be perpendicular. The electron field direction is perpendicular to the wave propagation direction, and the same thing for the b. Is really is just the amplitude is just different by 1 over c. Okay, and it is really in phase. Okay, with the electromagnetic with the electrical field, and the direction is really k times this n direction. Okay, for the example that I showed here, for this simple example, I assume the k direction is really z direction. I assume that this electrical field direction just along the y one, and you can see that k cross n will become this x direction, this becomes y direction. Okay, so the magnetic field should pointing along the y direction for this case. Okay, and you can see that so here is really e is because e is along the z direction, e is along this n direction, so e is perpendicular to the wave propagation one. B, of course, is this direction is k cross n, and we know that the cross product give you a vector that is perpendicular to k and also n hat. Okay, so this one we also have 0 there, so that really means the electric is E and B are both transverse. Okay. Okay. So that is what we have. Just for wave propagating in a general direction. Okay, not just along the z direction. Okay. Now we talk about the energy and momentum in electromagnetic wave. Okay, so we mentioned that the energy per, we talked about this before. So we have the electric field, we have the magnetic field, and we mentioned that they both containing energy. I said the energy per unit volume in this electromagnetic field really is, you can look at this, is a V 1/2 epsilon E0 plus 1/2 1 over mu 0 b square. Okay, so this is really the energy that are stored in the electric field, and this is the energy that are stored in the magnetic field. Okay, so we said for a monochromatic wave, we said this B is really related to E. Okay, B is really just really E divided by C. Okay, so now you can see that here is B square, here is E square. So you can see that is B square is really E square divided by C square. And we said 1 over, remember that C is really mu 0 epsilon 0. Okay, so here is really mu 0 epsilon 0 E square. Okay, B square is really equals to that. So now you can see that mu is really the first one, epsilon is 0. So this is the electrical one. Now for the magnetic one, okay, because B square is equals to this mu 0 epsilon 0 E square. And you see that mu 0 cancel with each other. So this side also give me epsilon 1/2 epsilon 0 E0. Okay, you can see from here. So this is just shows you that for a monochromatic plane wave, the electric and magnetic field contributions are really equal to each other. Okay, because each one is half, so we really just have epsilon 0 E square. Okay, and we said for the E is really we have the magnitude. Okay, and we also have the wave one, which is cosine omega t kz minus omega t plus some phase angle. Okay, so this is really just tells you what is the energy per unit volume in electromagnetic fields. Should look like this. Okay, so as wave propagates, okay, and it carries the energy along with it. Okay, then last time we also talk about the energy flux density. Okay, which is really the energy per unit area per unit time. Okay, so we also talk about we have electromagnetic wave just propagates in the field, and they are we when we talk about this work energy theorem, for the electromagnetic waves, we really talk about the Poynting vector. Okay, so which is we said defined as S is 1 over mu 0 E cross B. Okay, so this is you can think about that. If we said if we have a volume, so there are some energy that are carried by the electric field and magnetic field, and then of course for the volume, so there are surface, so there are energies that are coming out through this surface. Okay, and then we really have the work energy theorem, to have for the energy conservation, kind of like things like that. Okay, so this is the energy flux density, which is really defined as energy per unit area per unit time. Okay, so it's defined as that. Okay, and we know that E, as let us consider for the x direction one, and B is then let us consider this case which one is x direction, then b is y direction, and then the wave, the energy flux density, we are pointing along the z direction. Okay, and then we really have mu zero. Remember that b and e are just different by 1/c. Okay, so this is along the z direction. Okay, so 1/c is really becomes so it's something like that. Okay, so yes, so c is really this. Okay, so c square is really mu 0 epsilon 0. Okay, so 1/c is really mu 0 epsilon 0 divided mu 0 e square z hat. So this one really becomes epsilon 0, so becomes no, so this is becomes oh yeah, okay, so I see some mistakes here. Yeah, okay, so that is fine. Yes, so I should really write it down this way. Okay, I should really write it down this way. So we can write it down this way. We can put epsilon 0 here. Okay, so this side is still the same, e square z hat. Okay, so the reason I can do this is it's 1/this, if 1/this mu 0 epsilon 0 becomes c square. Okay, so I have this. So this is c, one of the c cancelled. So c epsilon 0 e square z hat. Okay, and we said this epsilon 0 e square, okay, is really the energy density. Okay, and the energy that per unit volume. Okay, so this is really becomes c times this u z hat. Okay, which is actually what we expected. Should be, because the wave is propagating. Okay, so the flux density should be really the energy density times the velocity of the wave. Okay, so that is what we should expect to have. Okay, so this one I didn't describe it before, but I just say the momentum density. Okay, that are stored in the fields. Okay, is really, let us call it G. Okay, so this G is really related to this Poynting vector. Okay, S, and we only divide it by 1/c square. Okay, so you can look at the chapter 8 to find this equation. Okay, so now it looks like this. So just for this monochromatic wave, you see that because S is really just this, so this one is really U/c. Okay, that are along this z direction. Okay, so this is what we have. Okay, and of course this U depends on this magnitude of the electric wave, and this magnitude of course depends on time. Okay, when wave propagates at different positions, the amplitude because it times this E0 times cosine is really the final amplitude is different. Okay, because wave also propagate very fast, and the energy per unit volume and also the energy flux density is often different as a function is as a function of time, because wave also propagate very fast. So we are often interested in the average energy and momentum densities. Okay, so in other words that we know that when the magnetic electro wave amplitude is the highest one, we have higher energy density. When it's 0, it becomes the energy density becomes 0. Okay, so we often just average the energy, around one wavelength. Okay, because so in other words that we need to average this cosine theta square, okay, over a time period. Okay, and because that average is basically just 1/2. Okay, so we often put this, okay, parentheses there to indicate the average energy density. Okay, so this one average one is just 1/2. Okay, okay, so we only care about the maximum amplitude of the wave. Okay, the average flux density, okay, is 1/2 c epsilon 0 e 0, okay, along the z direction. Okay, and this average momentum, okay, is really 1/2c epsilon 0 e 0, also along the z direction. Okay, so this is what we have. Okay, okay, from here, because this is the energy density, okay, we mentioned that, so that can really be converted to the average power per unit area. Okay, so this is what we call the intensity. Okay, so this is really average power per unit area. Okay, transported by an electromagnetic wave. Okay, so this one is really, we use I to indicate that, which is actually just the average of the flux density. Okay, so which is really 1/2 c epsilon 0 e 0. Okay, so this is the intensity of a light wave. Okay, so now let us assume that we have a surface here. We have the light that heat this surface, and then so let us assume this is a perfect absorber. Okay, so the light, okay, being absorbed. Okay, so when the light hits this wall, it delivers its momentum to this surface. Okay, okay, and we can really calculate. So that is something we call the light pressure, or called the radiation pressure. Okay, so let us look at the average momentum, okay, that this light will give to this wall. So this is really just the average momentum showing here, okay, times the area. Okay, and let us consider a short time that c times d delta t. Okay, this is the average momentum that are transferred by the light to this wall. Okay, once we have this, then we can have so-called radiation pressure. Okay, which is really defined average force per unit area. Okay, so this pressure, okay, is really this one divided by the area. Okay, this is with respect per unit time. Okay, so we need to divide by delta t. Okay, so from here you can see that this one is really give us really g times c. Okay, so it's really give us g times c. Okay, okay, and because c is really this, so also give us 1/2 epsilon 0 e 0 square z hat. Okay, so it's just give us the pressure, that I like this. Okay, of course, if this wall is really a perfect reflector, okay, so that means the light hit there and then be totally reflected. Okay, So now you can see that the pressure is really twice as great than this case, okay, because you can imagine that the light is reflected the same way, and so that the pressure is 2 times bigger, okay, because the momentum now switched direction, okay, instead of being simply absorbed, okay. So this is just introduce these concepts, okay. Now let us consider, okay, so here we consider the ideal case, really the wave that are propagating the vacuum, and also we talk about monochromatic waves, okay. Now let us consider the electromagnetic wave in matter, okay. In matter is really, we know the equations that we described before, okay, and it's often very complicated. Let us only talk about linear media, okay, so it will be easier to handle. And we also consider the case that there are no free charge and also no free current, okay. We consider a simpler case, okay. So from there, we can really write down the Maxwell's equation, which is really like this: partial B over partial T, and del dot B equals to 0, and del cross H, okay, equals to partial D over partial T, okay. So these are really just the equations, okay, that are in matter with zero, with no free charge and a free current, okay. So now let us consider is a linear media, okay. A linear media is really just D is proportional to E, and this H is also proportional to B, okay. So that we get rid of D and H, and we only have equations that with E and B, okay. And we also assume this is homogeneous, so we really means this mu and nu do not vary, okay. It's a constant inside the material, okay. So once we have these assumptions, okay, then we simplify this equation, okay, because D is just proportional to E, and epsilon is really a constant, so we have del dot B equals to 0, okay. And here this equation is still the same, okay. Del dot B is also, this equation is the same, and this equation changes to mu epsilon partial E over partial T, okay. So it becomes like that, okay. So this one is really, if you look at the case that we derived for the vacuum case, the only difference is previously we have mu 0, epsilon 0. Now we just have mu and epsilon, okay. So that is the only difference, So previously mu 0 now becomes mu. Previously epsilon 0 becomes epsilon. So so that really means so the E and B will still satisfy the wave equations, okay. So the only thing is now the wave speed is previously is epsilon 0 times mu 0. Now the speed is really 1 over epsilon times mu, okay. And we can define that as a C over N, okay. And C, of course, we said is really 1 over this epsilon 0 mu 0, okay. So from here, we can get N is really epsilon mu divided by epsilon 0 mu 0, okay. So this is really called index of refraction, okay. And we know that for most material, mu and mu 0 they are very similar to each other, Okay, so they can cancel. So n at the end is approximately epsilon divided epsilon 0. Okay, and we know that epsilon is often bigger than epsilon 0 because this one is the value in the vacuum. Okay, so this one is really becomes epsilon r, which is really the dielectric constant. Okay, this is often is greater than 1. Okay, okay, because this n is greater than 1, so that really means v is less than c. Okay, so that really means that if the electromagnet the light can travel inside the matter, it only travels with a speed that is really determined by this. Okay, and is often lower than the speed of light. Okay, okay, and from here we can also derive the energy density, like what we derived before. It's exactly the same equation. Okay, so now the only thing is previously we have epsilon 0 e square, so now it's just epsilon e square. Okay, so here is 1 over mu b square instead of 1 over mu 0 b square. Okay, so now we also have this pointing vector. Okay, it's really s. Okay, is 1 over mu e cross b. Okay, instead of 1 over mu 0. Okay, okay, and also we often because here we are talking about a wave that are propagating in material. Okay, let us consider really if there are some surface, for example it can be air here, it can be glass here, for example. We have electromagnetic wave that propagate in the air and then hit this surface. Okay, and we know that the wave will be reflected and also transmitted. Okay, and then to figure out what happened. Okay, during on this surface. Okay, we need to use the boundary conditions. Okay, so the boundary condition is really what we derived in chapter 7. Okay, and we derived that before, and the equation said that if we consider the case there are no free charge and also no free current, the situation, let us say this is epsilon 1, this is epsilon 2, and what do we have? So this is this is the surface. Okay, we really define if you look at what we derived before, so this is what we have. Okay, we have epsilon, we have E1 in this material and E2 in this material. Okay, so for the components, okay, that is perpendicular, okay, to the surface. Okay, but perpendicular, for this case is really this direction. Okay, if this is an unhead direction, this direction, the E component along this direction. Okay, so it satisfies this. Okay, for B really is this. Okay, and for the E that are parallel to this surface. Okay, because it's parallel that really have two directions. Okay, if you can think about x, y. Okay, parallel to this surface is really have two components, so I put a vector there. This is really a two-dimensional vector. Okay, so the two vectors are really equal to each other, and also 1 over mu 1 b1 equals to 1 over mu 2 b2. Okay, this is for the magnetic field. Okay, and then next lecture I will discuss about how we can use these boundary conditions. Okay, to figure out how the light, propagate from one material to another material.